Hi, I'm Karthik Gopalakrishnan, and I'm going to talk about efficiency and fairness in traffic management for unmanned aircraft systems, or UAS for short. This is work done with Christopher Chin and Hamza Balakrishnan at MIT, and Maxime Agro and Anthony Evans from Airbus. So in the future, the skies are expected to get more crowded. And one estimate by Airbus says that in 2035, there are going to be almost 19,000 flights that are in the air at any given hour over Paris. Most of this increase in volume comes from autonomous delivery drones. So what changes? This increases the traffic volume and level of congestion. For instance, in 2020, we see about 1,500 flights in the air over the entire US. But in 2035, we are expected to see 10 times this volume just over a city. And this translates to almost a 6,000-fold increase in the density of operations. Secondly, this reduces the certainty in flight schedule. Today, we can book a flight almost a year in advance, whereas in the future, Amazon Prime Air has a vision to do package delivery using drones in less than 30 minutes. So to ensure safety, we should limit the number of aircraft that enters any given region of airspace or a sector. So in this example, there's a map of Boston, and each of these grid cells represents an airspace sector with a fixed capacity. So we want to ensure that the utilization at any of these sectors is less than the capacity for safety. So there are two approaches to limiting sector utilization. And the first and more classic approach is the traffic flow management, is called the traffic flow management problem. So the way this is implemented is that before the departure itself, you can take all the schedules of these flights, perform a large scale optimization to ensure that none of the sector capacities are violated. However, there are a couple of problems with this approach. One is that you need to know the schedule for all these vehicles well in advance. And this method does not computationally scale well when you have a lot of flights and a lot of sectors. In contrast, a congestion control protocol is more of a real-time tactical approach, which is based on a rules of the road kind of policy. Whether this is efficient or not, of course, depends on the protocol that we are using, but most definitely it's going to be much more easier to scale this congestion control protocol approach for larger problems. In this context, the first question we want to ask is whether the flight delays that are assigned are equitably distributed. Equitable distribution could be across the different flights themselves, or even across operators that are managing a fleet of these flights. Second, we want to ask what the trade-off between efficiency and fairness is. This means that when we try to assign delays equitably, we want to know what the total increase in system delays are. The main objective for our work is to compare both the traffic flow management approach and the protocol-based approach in terms of efficiency and fairness. So in the next two slides, I'll summarize the traffic flow management problem and some of the results that we have obtained in this regard. The setup is as follows. We want to assign ground and airborne delays for each of these flights before they depart itself so that sector capacities are maintained or are respected. So this is set up as a large-scale integer optimization problem where the objective is to minimize the sum of airborne delay costs, ground delay costs, and some measure of unfair allocation of delays. The constraints are the departure and arrival capacity at the airport or vertiport, en route sector capacities, and constraints on the vehicular performance, which is captured with a cap on the maximum air or ground hold, the vehicle speed, and maximum endurance. We have three main results in this regard. These are obtained by performing simulations on a package delivery scenario in Toulouse. The trajectories for the vehicles in this package delivery scenario is obtained from our colleagues at Airbus. The first result we have is that Significant improvements in fairness can be obtained with negligible decrease in efficiency. Second, we learned that there are a lot of ways of defining fairness in a network resource allocation problem, but not all of these metrics are similar. Some of them may even be orthogonal. This means that trying to maximize fairness metric X can actually worsen the fairness metric Y. The third observation is the most important in terms of how the traffic flow management problem can be adapted for schedules with really low file ahead times. So if we implement the traffic flow management problem at shorter time intervals, then we see that, of course, the efficiency decreases, but this does not necessarily worsen the fairness. The main objective for studying the traffic flow management problem is to compare the protocol-based approaches, which we will develop, to this baseline in some sense. I will now describe our ongoing work and findings for protocol-based approaches. I will use some notation to precisely define what I mean. X of t is the current sector for each of the flight. They are denoted using circles in this cartoon over here, and the color denotes the operator for that particular flight. X star of t plus 1 denotes the sector that each of these flights want to go to at the next time step. In this cartoon, they are represented using an arrow. The capacity of each sector is denoted as C. For instance, if the capacity of the sector is 1, then 2 flights want to enter this sector at the next time step, and the protocol should only allow one of them. So the objective here is to find a good protocol, meaning it's both efficient and fair, such that given the current sectors for the flights and their intended utilization at t plus 1, we can find a safe way to prioritize and allow certain flights to go ahead and access their next sectors. The high-level algorithm for our protocol is as follows. First, we identify cycles and prioritize flights along those cycles in order to avoid this problem of blocking. Second, we go over all the sectors in the decreasing order of their congestion level. And at each sector, we maintain and update a priority queue of flights that want to access the sector. And then depending on capacity constraints, we are going to allow only a certain number of flights from the head of that priority queue to enter the sector. There are different priority orderings that can be used, and that determines which flavor of the protocol we are going to be using. In the next few slides, I will go over 5 different priority orderings which we use in our study. Let us look at these priority schemes from the perspective of one sector, which has a capacity of 3. And since 2 vehicles are already in its airspace, it can only allow 1 more to enter its sector. A round robin scheme is the simplest, where it alternates between the different input streams coming into the sector. The second approach, which is back pressure, prioritizes the input stream that has the maximum back pressure, where the back pressure is simply the number of vehicles that are already waiting in a queue. The next scheme, accrued delay, maintains a single priority queue by merging all the input streams, where the prioritization is based on the accrued delay, meaning the flight at the head of the queue has experienced the highest delay so far in its flight. The next scheme has the same idea of a single priority queue, where the prioritization is given to a flight which has had the highest number of reversals so far in its trajectory. And just to clarify what I mean by reversal, if in the original schedule, flight A is supposed to arrive before flight B, but somewhere because of reordering and delay assignments, A arrived after B, then it's counted as one reversal. And then the last scheme we have is based on dominant resource fraction, where a flight that has utilized resources significantly in its prior trajectory would not be prioritized when a flight that has been most efficient and has had the minimal use of resources so far would be prioritized. I will now describe the setup for evaluating the performance of our protocols. The results are averaged over 100 simulations of this randomly drawn trajectory of 100 flights. We define the efficiency of our protocol as the sum of the delays assigned to all the flights and the fairness of a protocol as the standard deviation of the delays. The first question we ask is whether an operator should internally deconflict the schedules of flights that it manages. We find that although intra-operator deconfliction leads to fewer conflicts, it decreases the overall efficiency and fairness of the solution. This is true for all the prioritization schemes, and the results are shown in this table here. So what we are quantifying is the change in the efficiency and fairness due to intra-operator deconfliction. We see that the delays are all higher, the standard deviation is higher, and the number of conflicts decreases whenever there is intra-operator deconfliction. This result suggests that it's better for operators to directly use our protocol rather than try to perform any internal deconfliction before flying their missions. Next, we compare the performance of our different protocols using the figure on the right. Each dot represents a different protocol. The x-axis is the total delay in minutes. So point that's further towards the left is more efficient because it has lower delays. The y-axis represents the standard deviation of flight delays. So a point that's lower on the y-axis is more fair. Just for reference, look at this blue cross on the top right. This is a random prioritization of flights. So naturally, all our protocols do better than that random prioritization. In particular, note that the back pressure algorithm has the lowest total delays, and the accrued delay protocol has the lowest standard deviation. Although we did not talk about the dominant resource fraction in the previous slide, I want to highlight the slightly different traffic pattern, which will emphasize some of the key features of the dominant resource fraction protocol. So let's look at this figure where we have a lot of flights from operator 1 marked in red going in the east-west direction, and significantly fewer flights by operator 2 marked in blue going in the north-south direction. So it's clear that operator 2 has lesser demands on the system resources. Here, we see that the dominant resource fraction based prioritization really prevents the exploitation of operator 2, which has lower market share and lower resource requirements. This is shown on the figure on the right, where the y-axis is the mean operator delay. And we see that operator 2 gets the best solution, meaning the most efficient solution with the lowest delay only with dominant resource fraction. This brings me to the end of the talk. I want to emphasize that the protocol-based approaches, because of their ability to accommodate more dynamic traffic, offer certain benefits over the traditional optimization-based traffic flow management approach. However, some concerns with the protocol-based approaches are higher communication workload, lack of predictability, and the potential for entering into certain infinite negotiation loops. There's a lot of future work that needs to be done in order to evaluate these protocols entirely. First, we want to compare these protocols with the efficiency and fairness of these protocol solutions with the traffic flow management solutions. Next, we want to work towards proving certain performance guarantees in terms of the maximum delay that could be assigned in these protocols. And then finally, look at the more broader question of strategic behavior and competition between fleet operators and how it impacts some of these protocols.